Welcome to Techno Sapiens.
Happening. I want you to imagine a standard battery, and it's connected to two different wires, creating what we call a two-wire circuit. This incredibly simple setup is going to be our baseline today for understanding how current truly behaves when it's suddenly presented with multiple options. So we've got a really stark physical contrast between our two options here. On one side, we have path A, which is a short, thick copper wire. And on the other side, we've got path B, which is a long, super thin wire. Now, both of these paths connect the exact same positive and negative terminals of our battery. That popular myth we just talked about, it tells us that when we close this circuit, electricity will just zoom straight down path A simply because it's physically shorter. But that's just not how the real world works. When this circuit closes, electricity actually flows through both of them at the exact same time. It doesn't just pick one. To figure out why it flows through both paths and how it sort of magically decides how much juice goes where, we really have to look at resistance. Basically, it's the electrical pushback. Now look at this formula. Resistance equals resistivity, which is just the actual material the wire is made out of, times the length of the wire, and then divided by the area, or basically the thickness of that wire. So every single path in the universe has its own unique resistance that's entirely dictated by these specific physical traits. So what actually cranks up that pushback? Well, a longer wire intrinsically pushes back more. A thinner wire pushes back more. And obviously, a poorer conducting material pushes back more. So jumping back to our circuit, path B is long and thin, right? That physical nature guarantees it has a really high resistance. Path A, on the flip side, is a short, thick copper wire. And copper is a phenomenal conductor. Therefore, path A allows the current to just flow much more easily. Its resistance is drastically lower. All right, so we know the physical properties of the wires that cause this resistance, but now we've got to look at the foundational physics governing the actual flow of the electricity itself. Enter Ohm's law. Guys, this is literally the golden rule of electricity. Ohm's law states that current equals voltage divided by resistance, period. If two paths share the exact same voltage, like, say, being hooked up to the exact same battery, the path with the lower resistance is going to carry more current. It's a direct, immutable mathematical relationship. There's no getting around it. Let's actually put some hard numbers to this so we can really map it out. We are going to set up a scenario using a standard, everyday 12-volt battery. Imagine we take those 12 volts and we connect them to two parallel paths, just like our earlier example. But this time, we actually know their exact electrical resistance in a unit called ohms. And this brilliantly illustrates Ohm's law in action. Watch how our 12 volts perfectly divide based on the resistance of each path. Path A has a super low resistance of just 2 ohms. So 12 volts dividing by 2 ohms, that gives us 6 amps of current just flowing freely through it. Now, path B has a much higher resistance of 6 ohms. So 12 volts divided by 6 ohms gives us just 2 amps of current. The mind-blowing part here is that the current is flowing through both paths at the exact same time. But purely because path A offers less pushback, it ends up carrying 3 times more current. What this fundamentally means, and this is so important to grasp, is that electricity is not making a decision. It really doesn't look at a fork in the road, ponder its life choices, and then pick one path over the other. It is simply blindly following the rigid laws of physics. It divides proportionally based entirely on impedance and resistance. It's just a completely automated mathematical response to its physical environment. Now, truly understanding this concept brings us to the real physical stakes of this explainer. Think about it. If current inherently scales based on resistance, what happens when a circuit bypasses all normal resistance entirely? Like, what happens to the math when the resistance drops all the way down to basically 0? Well, this introduces a highly dangerous, very real-world scenario that you've probably heard of, the short circuit. So in a normal, functioning circuit, current flows from the battery, goes through something like a light bulb, and then flows back to the source. That light bulb is actually providing safe, absolutely necessary resistance. It effectively limits the flow of current so everything runs smoothly and, most importantly, safely. But imagine a rogue piece of metal suddenly directly connecting the positive and negative sides of the circuit, completely bypassing that light bulb. Because there is suddenly almost 0 resistance left to hold that electricity back, the current just spikes massively and uncontrollably. And when current spikes like that, it escalates rapidly into severe danger. The extreme, unchecked flow of electrons causes rapid overheating in the wires. I mean, we're talking intense heat that leads to dangerous sparks, completely fried equipment, and very easily catastrophic fires. This exact physical reaction, this extreme spike in current due to a sudden lack of resistance, is precisely why we rely on circuit breakers and fuses in our homes. They're literally engineered to instantly detect that dangerously high current and physically break the circuit before a fire can even start. Okay, to really lock this concept in, we can look at a perfect parallel in the physical world: plumbing. I know it sounds weird, but the water pipe analogy is a classic for a very good reason. You can think of electrical current flowing through wires, exactly like water flowing through a system of physical pipes. Just like water, electricity is always looking to move through the system. If you have a wide open pipe, it allows a massive amount of water to flow freely with very little pushback, right? That perfectly represents our low resistance path, exactly like that thick copper wire from earlier. A narrow pipe, however, restricts the flow. It physically allows much less water through. That's our high resistance path. Now, if you pour water into a system that splits into both of these pipes, the water doesn't exclusively choose the wide pipe. Sure, a massive torrent rushes through the wide one, but a smaller trickle still makes its way through the narrow one. The flow divides entirely based on the restriction. So here is the absolute definitive takeaway rule for today. Electric current flows through all available paths. It does not just pick the physically shortest one, and honestly, it doesn't even just single out the easiest one. It utilizes every single path available to it simultaneously, with the lion's share of the current naturally flowing through the path that offers the lowest resistance or impedance. This foundational concept completely changes how you look at the engineered world around us. Seriously, next time you flip a switch in your home, will you see those invisible rivers of current dividing and distributing all around you? Remember, electricity always follows physics, not shortcuts. It respects resistance, not distance. I really hope this explainer has sparked a brand new curiosity for the hidden mathematical forces powering our everyday lives. Keep learning, keep asking great questions, and I will see you in the next explainer.